Welcome to our webinar on making smart injection molding resin selections. This is produced by Ferriot Incorporated. Thousands of different injection molding resins are available to choose from when creating a new injection molded plastic part or transitioning from a part from metal to plastic. To make the smartest resin choice for your application, start the selection process with your part producer as early as possible in the development cycle for your part. The longer you wait to choose a resin, the higher the likelihood of disappointment with some element of the final part. Making resin selection decisions under time pressure can end up costing you more money in the end through less than optimal part quality or appearance, part failures, high rejection rates, or end product recalls. Part geometry, mold design, and resin choice must be developed concurrently. Your resin selection process should start with an extended, no secrets conversation with your injection molded part producer. Enter this conversation without preconceived biases about which specific resin types are most appropriate. The resin used successfully from a previous part may not be appropriate for a new part configuration or application. Make sure your injection molded part producer is aware of all the conditions to which the finished part will be exposed, such as UV exposure, heat and cold, chemicals, radiation, mechanical loading, and the such. If the finished part must pass a specific test procedure, your injection molding producer needs that information early in the resin selection process. You and your injection molded producer need to identify the most critical characteristics of the finished parts as soon as possible, even if it doesn't initially seem relevant to the resin selection process. Define how the part will be used. Is it a standalone part or a piece of a larger assembly? Does it need to match other parts used elsewhere in an end product? Will the part be an industrial or consumer product? Understanding the industry and how the end user will interact with the part will affect both the design and the materials used to make it. Your part's mechanical loads, including short-term static loads, vibration, cyclic loads, and impacts, must be carefully considered in the resin selection process. These loads could lead to part fatigue. Long-term overloads can lead to creep and stress relaxation. Once these characteristics are identified, you and your injection molding producer can work together to weigh the resin options available. Before attempting to choose a resin, you and your part supplier should take the time necessary to analyze your part's geometry. Part size, shape, and wall thickness can make the part especially prone to warpage, bow, and other defects. The sooner your parts producers' engineers can review the part configuration with mold flow analysis and suggest changes to optimize its moldability, the earlier you can begin to narrow the list of appropriate technologies and resins for that part. Weigh which molding technology is most suitable for the part. Traditional injection molding is typically done in two stages. In the injection stage, melted thermoplastic is injected into the mold. In the packing stage, pressure is applied and the plastic is formed into the shape of the mold. Parts made by structural foam injection molding can replace many types of materials, including metal, wood, concrete, and fiberglass. In structural foam molding, the injection stage is basically the same as in traditional injection molding, but the packing stage employs a chemical blowing agent mixed with the thermoplastic material to create thermoplastic foam. That chemical blowing agent is triggered by heat and pressure and expands the material by creating a rigid microcellular structure to form the parts against the mold. These parts aren't as dense as traditional injection molded part and can be as much as 10 to 30% lighter, while still retaining its durability. Structural foam molding also scales well, so large or bulky parts can be manufactured quickly. Structural foam molded parts also offer an excellent stiffness to weight ratio for added durability without added weight. The gas assisted injection molding process involves injecting an inert gas into an injection molded part during the packing stage. The process employs compressed gas as the packing medium, providing dimensional stability for thick molds and reducing warp and sink marks. This technique uses less injection pressure and can reduce clamp tonnage requirements, saving on the amount of energy and cost required to produce them. Overmolding is the process of combining two or more molded plastics or elastomer parts to make a single finished part. It is often added to modify the texture, color, or functionality of a part. When selecting the right resin for your part, you need to consider what your overall design goals are for that part. Is it reducing weight, consolidating an existing assembly into fewer parts, or are you incorporating mold-in assembly features, improving the strength to weight ratio, cutting manufacturing costs, or are you eliminating painting or other surface treatment options, improving impact or chemical resistance, providing a longer lifespan, or will the part need disassembly during its lifespan? Once your goals are defined, you're on your way to defining which resin or resins is the right choice for your part. Define the key physical attributes required of the finished part, including how it will be used and the hazards it must withstand. Describe the environments in which the finished assembled product will be used, stored, etc., including the full range of end-use environmental temperatures. A molded part's impact and tensile strength, creep resistance, modulus, and other material properties often vary greatly depending upon the temperatures to which it is exposed. Understanding these levels of weathering the part will be exposed to will narrow the list of appropriate resins. Knowing the environment in which the finished part will be used simplifies choosing a resin designed to withstand potential damaging substances like automotive fluids, cleaning solvents, cutting oils, degreasers, lubricants, mold releases, paints, adhesives, printing dyes, and cooking greases. Outline the types of chemicals to which the part will be exposed during manufacturing assembly and its intended environment, and make sure the resin you choose is compatible with or can at least withstand these chemicals. Assess the impact of the part's electrical environment. What kind of electrical load will it be subjected to? Will the part require EMI shielding or UL testing? Evaluate radiation exposure. Radiation from HID lamps, fluorescent lamps, gamma sterilization units, or other artificial sources can affect the strength and appearance of the parts. This involves radiation from ultraviolet, infrared radiation, electromagnetic interference, radio frequency interference, and more. UV stabilization resins may be required. Describe the part's required flexible strength, impact strength, and fatigue resistance. Include the required flammability ratings. Your part's desired appearance plays a major role in both part design and resin selection. Identify the required color, texture, and gloss level. Standard surface finishes range from high gloss to heavy matte. Is it necessary to match the appearance of a component made of another material? Will the part be painted, plated, hard-coated, textured, or something else? Do you need a custom resin color to comply with corporate or industrial standards? Keep in mind that custom resin colors will cost more than standard colors, particularly in smaller quantities. Other special finishes, treatments, decorations, lettering, are they required? markings, logos of warning, instructions, and control labels. If you need a transparent part, the range of resin options is greatly reduced. The required finish for your parts plays a role too. Metallic finishes can require painting, in-mold decoration, or vacuum metallization. If the part must maintain a specific color over its lifespan to match the color of other parts in a final assembly, the resin selected must be resilient enough to weather and wear at the same speed as the other materials without yellowing or otherwise discoloring. Start now to narrow down the possible resin types for your part. Thermoplastic resins come in two basic classes. There's engineering grade resins, and then there's commodity resins. Engineering grade resins, such as nylon. Nylon is tough, superior thermal and chemical resistance, plus a wide variety of grades available with broad scope of physical properties. Another is polycarbonate. It's strong, high flex modulus, good temperature ratings, transparent for lenses and multiple colors. Then there's ABS. It's got great impact strength, superior surface quality, good colorability, good rigidity, with electroplatable grades available. Continuing on with the engineering grades, we've got PCABS. It's got good processability, toughness at low temperature, and superior dimensional stability. TPE is another. It's soft touch, rubber replacement materials, good tear strength, and good flexibility. TPE materials can be reground and recycled, unlike thermoset rubbers such as EPDM. Additionally, TPEs, like Santoprene, are less dense than their thermoset counterparts, EPDM. And there's acrylics. Transparent, good for some outdoor applications. And acetals, excellent wear resistance, great for gears and high wear applications. And structural foam. It's an excellent material to use and where metal replacement is considered. Good weight to stiffness ratio. Next, we have the commodity resins. Polypropylene. It's a versatile material, variety of grades in homopolymer and copolymer classes. Good fatigue resistance, excellent chemical resistance, and a lower cost. Polyethylene. It's very versatile, low cost material, variety of grades in linear low density polyethylene, low density polyethylene, and high density polyethylene. It's tough, weatherable, and easily processed. Next, we have polystyrene. It's available in general purpose and high impact, HIP, polystyrene, lower cost, range of impact from low to high, good clarity in general purpose grades, and good rigidity. Then there's polyvinyl chloride, PVC. It's low cost, chemical resistant, can be colored, weatherable, and natural flame retardancy. Document and dimensional tolerances for the parts. Tight tolerances are often required to ensure proper fit and function of an assembly, and different resins will shrink at different rates as the parts cure. Depending upon your part's use, it may need to be tested to meet standards set by various governmental and/or private agencies. See above, you've got UL, CSA, DIN, NSF, EPA, AHAM, AMMA, WEEE, RoHS, ECO, ASTM, FDA, OSHA, NIOSH, then federal regulations, ANSI, SAE, FMVSS, ISO standards for medicals, etc. These requirements will likely factor into the resin selection. Estimate the number of parts to be produced in each production run, as well as annual usage. This information might be helpful in determining the most appropriate press to use and help determine the most cost-effective choice of resins. The plan to produce a short run of the part, typically 100 parts or fewer, with the chosen resin before proceeding to a full production run is advised. To produce prototypes from several different resins to determine which ones offer the best performance and appearance for the application. It's strongly recommended for new parts or for old parts being made with a new resin. This helps your parts producer to establish and refine a high-quality manufacturing process. And it allows you to qualify, test a limited number of parts to ensure they satisfy your design criteria. Work with your injection molding producer to identify, qualify an alternate resin or backup resin at the same time as you choose your primary resin. Identifying an alternate resin eliminates the scramble to identify and source a new one if there's a shortage of the primary choice, and reduces the risk of making a less than optimal choice. The resin's producers' difficulty in obtaining raw materials, labor disruptions, sudden price increases, natural disasters, computer equipment malfunctions, a faulty change, a forced shutdown, or other governmental action, or many other reasons can cause resin shortages. Your parts producer should strive to optimize the primary resin for whatever balance of properties are important to you. The alternative or backup resin will also involve some level of compromise. Higher price, longer lead time, some compromise on more performance characteristics. Getting into the resin selection process early and with an open mind is the best way to ensure an optimal and cost-effective choice that meets your most important design objectives. The COVID-19 pandemic, combined with hurricane season and historical winter storm Uri, has created a national resin shortage that our country is actively seeing the effects from as we continue to battle with limited resin supply. Through this shortage, plants have been unable to produce and ship essential plastics, causing long lead times, shipping delays, and product limitations as the resin market works to manage the increasing high demands. As we continue navigating the national resin shortage, make sure you are acting appropriately to combat this crisis. We recommend when selecting resins, you specify alternate resins you can utilize and get them qualified. Provide an extended forecast for production. Consider making long-term commitments on orders and resins. Provide ample lead time on orders and prepare for cost increases. Thank you for watching our webinar. To learn more about resin selection and other injection molded topics, visit Ferriot.com. There you can download a free copy of our handbook on designing injection molded parts or our resin selection workbook, or subscribe to our blog. Thank you for listening, and we will now have questions and answers.